Hello everyone, welcome to the lecture 19, and in this lecture we're gonna talk about the settlement in soil. The subtitle is compressibility of the soil. This is the part 1, and in lecture 20 we're gonna continue talking about the settlement and the compressibility of the soil. So the learning objective of this class is to understand the deformation in saturated soil. So we'll see what causes the deformation and the mechanism of it, and estimate the total stress and pore water pressure and the effective stress during the consolidation, which is a type of deformation in saturated soil. And lastly, we're going to identify the elastic and the plastic deformation at the grain scale. So let's start. So on the ground surface, let's say that this is the ground surface, and a kind of structure with its own weight will be built. Then because of the weight, the stress state in a soil at a certain depth will increase, and this will compress the soil mass, and it will cause the settlement. So then the question here is, there are two questions. One is how much settlement will occur. And second question is then how fast it will occur. And these two questions are very important. And first one will be related to the serviceability of the structure. Right? If the settlement is too much and excessive, then the structure can be damaged. There could be some crack, and also it can have this uneven deformation, so that you have some tilt. And inside the if you have a machinery or residential area, then people will not be able to live inside. And the second question is, like, for example, the settlement occurs, eventually it's gonna occur maybe 20 centimeter. Then how long will it take to reach the 20 centimeter settlement? Will it take 2 years, 10 years, or like 2 months or 2 weeks? So, and this will be related to the cost of the construction. Right? Should we wait until it settles, so like 90% of them or 50% of them? That kind of a decision we'll have to make. So in the lecture 19 and 20, we'll talk about this question. We'll see how we can estimate the ultimate settlement, especially the ultimate consolidation settlement in the soil. And lecture 20, so this is lecture 19 and 20. And here the lecture 21 and 22 will learn how to estimate or predict the settlement rate using the consolidation theory. Okay, let's move on. The deformation of dry soil. Let's say that you have this kind of, in a container you have a dry soil pack, the dry sand, and sigma naught is the initial stress. So the stress was applied initially by the sigma naught, and soil was compressed with that load. And when you increase this load by delta sigma, so now the total stress is sigma naught plus delta sigma, then what will happen? The soil will be compressed. Soil will compress. Then when this delta sigma is small enough, then this load will cause only the elastic deformation. So that the deformation of the grain, so at the grain contact, it's gonna deform like this. And when you remove this delta sigma, then it will come back to the original height. So this is called the elastic deformation, which is recoverable when you unload it. And when delta sigma exceeds some threshold, so that you're applying now the large delta sigma, then particle will rearrange to cope with the given stress. So deformation will occur in association with the particle rearrangement. And when you remove this delta sigma, will this particle go back to the original position? It will be unlikely, right? So it's called irrecoverable deformation. And we know this term, plastic. So elastic deformation is just as shown in here. It will be a compression at the grain contact, right? And when the load is removed, then it will go back to the original shape. So it's elastic deformation. And if the particle moves actually to a denser state or to some large void, then this particle rearrangement will not be recoverable, so it's called a plastic deformation. Okay, that was the deformation in dry soil. And what about the deformation in saturated soil? Now you have water, right? So here, let's imagine that this is the initial state. You have sigma naught, which is the total stress, and the soil is full of water. And so there could be two different cases when drainage is not allowed. So there is no hole here for the water to escape. And when you apply, sorry. So I think we gotta start from the zero. So there was no, the total stress was zero at the initial. And then it becomes sigma naught. And this sigma naught total stress will be taken by the water when the drainage is not allowed. So the water takes up the most of delta sigma, the load increment. And this delta sigma transfers to the delta U, so that you have an excess pore pressure. So initially, here we go. Total stress is given by this much, sigma naught. And at that time, the pore water pressure was U naught. So the effective stress was U naught minus, sigma naught minus U naught. Right? When delta sigma is applied, total stress will be sigma naught plus delta sigma. So this is the load increment. Right? And because the pore water pressure, the water will take up the most of the stress. So pore water pressure will increase by delta sigma. So then if you subtract the pore water pressure from the total stress, you get the effective stress. So then still it's the same, right? U naught and the sigma naught minus U naught. So this is the load increment. Huh? So here and here you can see that the pore water pressure is still constant. So the effective stress is constant. So effective stress stays constant because of the increased pore water pressure. So you can think of this case. So there's a loading plate and there's a spring, which is the soil skeleton, and the void space is full of water, which is incompressible. And when you increase the delta sigma, the total stress by delta sigma, because there's no hole and there's no small hole for water to escape, so then the water pressure will go up. But when the drainage is allowed, So here I just punch a hole, the little hole there, and then water will start to flow out. So water will squeeze out while the solar skeleton get compressed. So then when you think about the pore water pressure, this pore water pressure will decrease with time. So look at the sand case. When delta sigma is applied, pore water pressure will increase by delta sigma, and then because the water is escaping, water gets squeezed out, so the pore water pressure will decrease and it will go to the original state, U naught. And rate of this reduction in pore water pressure will be different for different soil, and which will be functional permeability. So for sand, it has a high permeability, so the water pressure reduction will be instantaneous. And for the clay, because it has a low permeability, it can take several days to several years. So in this, the spring analogy, the size of the hole here that I'm punching it through is represented, that's representing the pore size and also the permeability. So then what will happen to the stress state in this case? So we have a drainage hole. Initially, its total stress is sigma naught, and the pore water pressure is U naught. So the effective stress is U naught minus sigma naught minus U naught, which is sigma naught prime. When the delta sigma is applied instantaneously, then the total stress is increased by delta sigma, so sigma naught plus delta sigma. And the pore water pressure, initially the water will take the most of the stress. So then U naught plus delta sigma, and then the effective stress will be the same because it will cancel out. The delta sigma will be removed when you subtract the pore water pressure from the total stress. So from here, but with time, it's gonna change. How? So this delta sigma, which is called the excess pore pressure, will dissipate as the water gets drained. So water squeezes out, so the load will be transferred to the spring. So U pore water pressure will reach to U naught, as we saw here, will go to the original state. Or if it's clay, it's gonna be slow, but still it's gonna go to the, it will eventually goes to U naught, the initial state. What about the total stress? Total stress doesn't change because we didn't remove any stress here. We didn't remove it, so it will stay the same. And then what happens to the effective stress? If we subtract the water pressure from the total stress, it will be like this. And we know that this 2 is the effective stress, so it's gonna be sigma naught prime plus delta sigma. So you can see that the effective stress is increased by this delta sigma. This total stress that's applied here, initially it's it was carried by this water, but with time it was transferred to the effective stress, which is the granular skeleton. So here water pressure is dissipated, or we call it dissipation of excess pore pressure. And at the same time you have an increase in effective stress. So again, if we go back, come back to this diagram, initially this delta sigma was taken by this water, but as the water is escaping, this delta sigma is transferred to this spring. So soil skeleton or the soil grains will carry the load increment. This is what happened in the deformation when you apply the load in the saturated soil. And this process, the compression process of the saturated soil, which is controlled by the rate of the excess pore pressure, is called the permeability, the consolidation. So the compression process of saturated soil, which is controlled by the rate of excess pore pressure dissipation, is called consolidation. And this rate of excess pore pressure dissipation, or dissipation rate of excess pore pressure, will be determined by the permeability. Okay, there was very important definition about the consolidation. In general, when you have a layered strata like this, the sand and clay and sand, when there's delta sigma, the total stress increment by the weight of structure, this will transfer to the sand and clay and sand. So here, the total sediment will be Si plus Sc plus Ss. And Si is the immediate sediment in sandy layer, and Sc is the consolidation sediment in clay. So you have a Sc here, Si and Si. And also in the clay you have also the secondary sediment, here secondary consolidation sediment. This immediate sediment in sandy sediments or sandy layer can be estimated by the elastic theory, and you're gonna learn about this sediment estimation for the sand in the foundation engineering class, but which will not be covered in this class. And for the consolidation sediment, we're gonna cover it in the next lecture, and which is time dependent and then mostly occurs in the saturated clay. The secondary consolidation sediment is smaller than the consolidation sediment, and also it's minimal for the most clays, and there's no secondary consolidation sediment in the sand, but still there are some cases that are very significant. Sorry about this typo, it should be S. So if you add all of them, then you get the total sediment. But in our class, in this C230, we will cover the consolidation sediment only, because that's the most significant sediment among three. Okay, in the coarse grain soil, you get the instantaneous sediment mostly, Si, because the water does not affect the deformation in the coarse grain soil, because the water, water can escape very fast because of their high permeability. In clay, also in fine grain soil, if it's saturated, consolidation sediment is the significant part, the major part. And if it's dry clay, it's very unlikely to meet the dry clay, but it will behave like a sand. And in this case, the deformation will not be time dependent. But the consolidation sediment will be time dependent deformation, because it will be controlled by the low permeability of that clay. Okay, so we just saw in this lecture the deformation in saturated soil And we saw the variations in the total stress, port pressure, and the effective stress during the consolidation. And also we saw the elastic and the plastic deformation. In here you have a grain contact deformation, but in here you have a particle rearrangement due to the large stress. Okay, thank you.